So, let us continue from last lecture, shall we? So, let us begin with the Taylor-Macol equation, which we derived in the last lecture, and then we will go ahead and see how we can solve for it. Okay, we will do a problem. Okay, so let me write this down from just to remind ourselves basically. Okay. Okay, so this was our Taylor-Macol equation which we derived last time. Now, when we start to try and solve this, let us do this. Okay, let us define this non-dimensional parameter. So, let us define here. Okay, this is just a non-dimensional parameter. So, let us define here, and when we do that, let us see what we get. Okay, so I am just going to sort of write this down. So, what we get here is this. Okay, let me rewrite this. So, what we get as the equation is this. Okay, and this is the first first bracket. So, basically I divide throughout by V max square, right. If I do that, what I get is okay, and V r dash is nothing but V r by V max. Okay. So, then this is my first bracket. Similarly, the second one, okay. That, and finally the last bracket. Okay, so this was actually our equation 5 like we did last time, and let us call this as equation 6 say. Okay, so basically what we have this Taylor-Macol equation which cannot be solved in the closed form. So, we have to revert to or use numerical methods to do that. So, in lieu of that, what we are doing is we are introducing this non-dimensional parameter V dash, which is this, and accordingly I have been able to transform equation 5, which is the Taylor-Macol equation, to this. Okay. Now, let us also look at what we did last time. So, when we introduced V max, okay. So, enthalpy constant, right. So, we can write this, right. If I can write this, so here let us say what I will do here. So, this also I can introduce this, right. So, let us do something here. Let us what we'll do over here is, let us divide by v square throughout. Okay, let us divide by v square throughout, and what we get here is that this. Right. So, I divided this equation by v square throughout. I divided this. So, you can see what we tend to get over here. Okay. So, therefore, what we get over here is, so this is Mach number, right. Is that fine? So, this is Mach number. Well, we can write this as 1 by v dash square also, you know. We can write this as well. Now, from here basically, so if I were to write this, therefore, I will write it in terms of v dash. So, therefore, v by v max, right, v by v max, which is equal to v dash, is therefore equal to right. So, this is what we get. Okay. So, this is a relationship which is interesting. So, let us call this as say 7. So, what we basically have done is developed got some relationship of this v dash parameter, which we have just introduced, with the Mach number. So, given the Mach number, we can, if you see from this relationship, so if the Mach number is given, okay, we can calculate v dash and vice versa. Okay. So, let us see whether we should be able to use this relationship in our solution to the Taylor-Markov equation. Okay. So, let us begin by looking at a problem. Okay. So, let us say, so we have say a 15-degree half angle cone at 0-degree angle of attack in a free stream with Mach number of 2. Okay. So, we need to find out the shock wave angle, the pressure, temperature, density and Mach number immediately behind the shock wave and on the cone surface. Okay. So, essentially what the problem is that we have say a cone like that. Okay. We have a cone like that. So, we have a free this okay. So, I have a cone, okay, the a line of symmetry, and this cone is inclined at 0 degrees to this free stream, which is Mach number is 2, and the cone half angle, this cone half angle is given to be 15 degrees. Right. So, what we need to find out is the shock wave angle. So, basically when we have a shock wave over here, so when we have a shock wave angle over here, what we need to find out is the shock wave angle, okay, and the properties of the flow immediately behind the shock wave and on the cone surface. So, essentially what we are talking about is that if I take several, say, radial lines, right, like we discussed yesterday. So, if I take, say, radial line, say, just behind the shock wave, then we will have several ones in the middle, and finally one which is on the body of the shock wave. So, what we need to find out is the properties. So, pressure, temperature, Mach number, density, etc., right, behind the shock wave, and then move from there, and as closer we get to the to the cone, and here also on the surface. So, then we also need to find out the properties on the surface, like we discussed yesterday, that these properties are going to change in this direction, in the theta direction. However, on a single radial line, these properties are going to remain constant. So, our problem here is basically, the problem to do here is that we have a 15-degree half angle cone which is inclined at 0 degrees to this free stream Mach number, Mach 2 flow. We have a shock wave. So, first job is to find out the shock wave angle theta s, and then the properties just behind the shock wave and on the surface of the cone. So, this is our problem. So, how do we go about doing this? Okay. What I am going to do is list step by step, okay, as to how we are going to go about this. Okay. All right. So, let's begin. Okay. So, let us say let us do this. Okay. So, we have a Mach 2 flow, okay, and the way we are going to solve this problem is like in an inverse fashion. You will see what I mean by that. Okay. So, step 1 is this is given. Okay. So, let us assume, so here let us assume theta s. Step 1. Okay, just assume theta s. Okay. Once we do that, okay, so theta s is theta s is the shock wave angle, which is essentially the beta, which we had learned earlier for the wedges, right, which was the theta beta m relationship. So, now if we do this, basically now what we will do here is calculate, okay, we will calculate, right, mn1, which is the, so in order to use, so we have an oblique shock here, right. So, we are going to use the tables, the tables to calculate the properties. So, in order to do that, I need to know the normal component of the velocity, normal component of the free stream, right, mn1, and if you remember, right, so mn1 right. So, this was the expression which we used last time. So, mn1, okay, so the normal component, so I have this, so then I will, okay, this is inclined, so I am going to find out the normal component of this. So, this is my mn1, right. So, mn1, and in this, so this is a sine beta, which in this case is, so in this particular case, of course, it is right. So, in here, so now m infinity, the free stream Mach number is given as 2, and theta s is something that we have assumed. So, therefore, I get a corresponding mn1 for this. Now, then we go ahead, okay, and look up the charts, okay, and get the corresponding mn2, right. So, now here the next thing to do is from the charts, okay, from normal shock tables rather, from the normal shock tables, we get mn2, right, and hence we get m2, which is correct. So basically, if I have the free stream come in here, and there is a certain deflection like that. So this is my m1 and this is my m2, right. So this is what we have done so far for an oblique shock. So we'll do pretty much that. So from here what we get is the Mach number behind the shock wave. Okay. Now let us just for a moment step back and look at the difference between a 3D picture like this and the 2D thing which we've done earlier. Okay. In order to do that, let us just look at this. Okay. All right. So let me go ahead and write that up here. Do that here. Okay. Okay, so this is the picture which we had earlier, right? This was our 2D picture. Okay. Okay, so we have this, right, and then say we had a shock wave out here, okay, and then we say had a shock wave like that. This way, right. So if we do and say this is our free stream, okay, so this is our free stream. So here this was the theta, right, this was the theta, this was the beta, right. And so now say if I have, so say I have this, okay, I have the free stream come in here, right, then it would deflect, okay. So it would deflect and this would make an angle of theta, right. So this is what we've done so far. This is the 2D picture, right. So this is the this 2D wedge picture. Now let us look at the 3D point of view. So what do we get here? Now 3D here, okay, this, and again we have a shock wave. Okay, this is a shock wave. So then, and we have the free stream coming in here, okay, and okay. So now in here, okay, so in here, now this is my half cone angle. This is my half cone angle, okay, and this is the shock wave angle, okay. You see the difference, this is the analogous to the beta over here, okay, shock wave angle, okay. So now let us do this here. So, therefore, so say I have the free stream come in here. Okay. Okay, and let us draw a line which is which is basically parallel to the surface of the cone. So, which is say this, or which is say this. Okay, and this line is essentially theta c. Okay. Now, however, now this free stream which comes in over here, okay, it does not necessarily have to deflect by theta c. Okay. So, therefore, it is say it deflects like that, okay, and this is say some and this it makes an angle say here delta. Okay. So, you see the difference between the 2D wedge and the uh, 3D cone. Okay. So, what happens here is the free stream comes in here, deflects by an angle theta, which is essentially the half wedge angle here. On the other hand, the V infinity here comes in, it does not necessarily have to deflect by theta c, it deflects by some angle delta, which is not equal to theta c. So, therefore, what we sort of see over here, so they both have the same cone, they both have the same angles, right. So, theta here, which is the cone angle here, is equal to theta c. Okay, they have the same cone angle, which is equal to the same half cone angle there. Okay, in terms of the similarities. Okay. The shock wave angle, of course, is not the same. If you have a 2D wedge, the shock wave angle is going to be different than if you have a 3D cone. So, therefore, this beta and this theta s are not same. Okay. And also, of course, the deflection angle, right, the deflection angle. Or rather, if I may write it like this, deflection angles are also different. Okay. So, essentially this would be, so this is to basically to explain this. Okay. So, now going back, so what we have done here is, so we have assumed theta s, and what we have been able to, we will basically use the normal shock tables and found out the Mach number behind the shock wave. Okay. Let us move to step 2. Okay. So, once we do this, let us move to step 2. Okay. Okay, if I do this, so now here, okay, so let me sort of draw a picture here. Okay, so now here, okay, so this is it, and then we have, of course, the shock wave, or let us say we have the shock wave. I am sort of exaggerating this a little bit. Okay. So, we have that. So, now, so therefore, this is my cone angle and this is the shock wave angle. Okay. Now, say we have a free stream which comes in. Okay. We have a free stream that comes in. right, and that is deflected let us call it that, and this angle of course is delta, right. This angle is delta and this angle is theta s, right. This angle is theta s. Now, we also know, which we did just now, okay. So, basically we have a velocity component in the radial direction and one in the perpendicular direction, which is this, okay. Now, so therefore, we could have several radial directions from here to here, isn't it? So, now let us say this angle. So, therefore, this angle here, so this angle here, we can call this as alpha, right, if I have this as alpha. So, now if you look at this picture itself, if you look at this particular picture, okay, so this alpha is nothing but the right. If you look at this, alpha is basically theta s, okay, minus delta. So, this alpha is theta s minus delta. If you look at this picture, this is the alpha, right. Okay. Now, again V dash of course is equal to this, right, and again of course this V r dash is V dash cos alpha and V theta dash is V dash sin alpha, okay. So, if you look at this picture over here, okay, so V dash, okay, V dash is essentially V r dash square and V theta dash square, and V r dash, okay, V r dash is V dash cos alpha and V theta dash is V dash sin alpha. If you look at this picture itself, okay. So, if you have this now, okay, if you have this, so therefore, now we will use this equation 7, okay. Now, what we will use is equation 7. Now, V dash is something that we need. Now, M2 is something that we have found out, right. M2 is something that we have found out over here. So, if we put M2 here, we will get the corresponding V dash, right. This is what we said. So, this is an equation which you can use. So, M2 is something that we have found out, okay, using the normal normal shock tables. So, therefore, if I use equation 7 now and input M2 here, I will get the corresponding V dash. If I get V dash, then of course, I can calculate the V r dash and V theta dash, okay. So, basically what what we will do here is that get V dash using 7, okay. So, using 7, or you can sort of do it here also if you want, okay. We can do it here also if you want. So, if we input this M2, okay, into equation 7 and get V dash, okay. So, there we are, okay. So, once we get this, okay, once we get this, so then the next step would be okay. So, step 3 would be okay. So, this is something that we had also written last time, right. Now, equation 6. Okay. So, I am now going to write this again. Basically, the Taylor-Markov theory, Taylor-Markov equation, when we wrote that using the non-dimensional parameter v dash. Okay. So, now we are going to use, if you see that equation, so that equation basically has just one unknown, which is v r dash. Okay. So, what we are going to do is now what we are going to do here is in step 3, okay, is that we are going to use that equation, okay, and calculate v r dash. Okay. We will calculate v r dash, okay, and in steps of theta, okay, in steps of theta marching away from the cone. So, what we are going to do is here, let us say use equation 6. Okay, using equation 6, okay, in steps of delta theta, okay, marching away from the shock to the cone. Okay. So, let me explain what basically we are going to try and do over here. So, essentially, so this is the shock wave. So, this v r dash is going to change, right, this v r dash. So, what we are going to do is when we have the Taylor-Markov equation, right. So, we are going to take that, okay, and we are going to take several radial lines here. Okay. We are going to take say several radial lines, okay, between this theta s and theta c. Okay. This is theta s and this is theta c, and we are going to move from here. We are going to start from here. Okay. Let us say, let us look at this picture over here. So, what we are going to do is we are going to take so on and so forth. So, what we are going to do is say on these angles are, say these are all delta theta. Okay. You do that. So, what we will do is we will start from here, calculate the v r dash, okay, and then again come onto this next, okay, come on to this next radial line, calculate the v r dash there, go to the next radial line, calculate the v r dash here, go to the next one, calculate the radial line there, v r dash there, and so on and so forth. So, we will start from here, we will start, okay, near the shock, okay, march away from the shock and towards the cone. Okay. So, calculate this v r dash in steps of delta theta. Okay. So, basically which means that we will calculate the v r at various radial lines, okay, between the shock and the the surface of the cone, right. So, when we do that, so we will have to solve the Taylor-Markov equation. Now, that equation, as you have seen, is the complicated one. So, we will come back to that. So, what we will do is basically use a fourth order Runge-Kutta method, okay, when we do that. Okay. So, having done that, so once we find out, v r dash, okay, once we find out v r dash, so what we are going to do is calculate v theta, right. If you remember, v theta this was, right. So, for each, so at each radial line, when you get a v r dash, you will also get a v theta dash. Okay. At each radial line, you will also get a v theta dash. Okay. All right. Now, So, now we keep doing this. Okay. Now, what was our problem? Now, our problem was that we need to find out the properties just behind the shock wave and on the surface of it, Okay. So, now, so when we start from here, okay, so we are going at various steps and we keep going farther and farther away from the shock wave, and at some point we should be reaching the surface of the cone, right. Okay, so like I said, this was like an inverse problem. So, we are actually beginning from here and coming back to the cone. Okay. So, now say at a particular theta here. So, we are moving away from it. So, say theta s, minus delta theta, minus 2 delta theta, minus 3 delta theta, so on and so forth. Okay. So, let us say, okay, okay, this is step 4. This is step 4. Okay. So, now say at we take, say, n number of, okay, so say number of so say the number of radial lines, okay, between here is, say, n. Okay. Say we have n radial lines, and and the angle step is delta theta. Okay. So, essentially n into delta theta is equal to alpha, is equal to theta s minus theta c. That is what it is. Okay. All right. So, if I do that, okay, now, so therefore, when I have, so therefore, okay, theta s, okay, minus n delta theta, right. So, when I get theta s, okay, minus n delta theta, I should have reached, right, I should have reached the surface of the cone, isn't it? Because what we have done here is that we are just dividing this space, which is the angle alpha, which is theta s minus theta c, right, and we just divided that space into n, using n radial lines, each spaced out at delta theta. So, therefore, when I now start back from here, so when I start from here, once I have covered this, right, once I have covered this alpha, which is theta s minus n into delta theta, I should have reached the surface of the cone, right. So, I should have reached this surface of the cone. Now, at the surface of the cone, so therefore, now at every step when I do this, at every step, at every radial line, I get a v r dash and I also get a corresponding v theta dash. Okay, we get these two velocities. Now, once we come here, once we come to the surface of the cone, so when we do this, when we have reached this, when we are doing this theta at this radial line, which is basically the surface of the cone, then we get a v r dash, of course. Now, what should this v theta dash be? Come to think of it, if you look at this, okay, this is v r dash, this is v theta dash. Okay. So, the radial line now, so essentially the radial line now is here, isn't it? The radial line is here. So, this is your v r dash and this is the corresponding perpendicular velocity component. In other words, does this make any sense? So, this is a solid cone surface and I have a component of velocity which is normal to it. What should it be? 0. So, we have to satisfy the 0 normal boundary condition here. So, as a result of which this v theta dash should be 0. Okay. This v theta dash should be 0. So, this is essentially the zero normal boundary condition that we are implementing at this particular point. Okay. So, however, obviously, so now in here, okay, so now this thing here, this theta s minus n delta s. So, this here of course, this should also be equal to 15 degrees in our particular case, right, because now this is theta c. So, theta s, right, we have done theta s minus n delta theta and minus n delta theta, that is now equal to theta c, is not it? This is theta c. So, in our particular case, this is given as 15 degrees. So, at 15 degrees, of course, v theta dash, this is should be 0. This is what one should achieve, but considering that this is a numerical procedure, obviously this is not going to be so. So, therefore, there is going to be a certain amount of error, okay, when we do this. So, when we reach 15 degrees, essentially we will have to implement the zero normal boundary condition, because that will then tell the numerical solution that I have reached the surface of the cone. Okay. All right. So, of course, there will be the error. So, now the reason is, now I should have reached 15 degrees here. Okay. Now, the reason, now what will happen is that I will not get this zero normal boundary condition. Now, why will the error creep in? What is the reason for this error? The reason for the error is that I have assumed theta s, right. I had assumed theta s for the given Mach number, I had assumed a theta s. So, what I have to do is to reassume this, okay, redo this, okay, in a better fashion, so that I get close to this 15 degrees as well as this. So, so this theta s minus n delta theta corresponding to v theta dash equal to 0. So, this to be implemented. So, I have to continue to iterate over this. So, once I continue to do that, so as soon as, so that I get close to this, I am never going to get completely 0. It is a numerical procedure, remember. So, there is going to be some errors, but we are going to try and get as close to this as possible, right. So, that is what we are going to do. So, we therefore continue to iterate, we will continue to iterate till we get this, okay. And once we get close enough, we within a say a 10 to the power minus 3 tolerance. So, then that is the shock wave angle. So, then that becomes the shock wave angle, which was also part of the problem. First thing what we wanted to know is what is the shock wave angle. So, then we would have correctly assumed, correctly estimated the shock wave angle. Okay. So, you see the difference here, unlike what we have done before, where we just look up the charts, that is not what we are doing here. Okay. So, we are going to therefore, we are going to assume and start, and then we iterate over this criteria, and then once this gets satisfied within a certain allowable tolerance, then we get our shock wave angle theta s. Okay. So, after that the stuff is about getting the properties, okay, behind the shock wave. So, once you come over here, if you remember, so I am going to stick to say, yeah, well, I got a couple of diagrams here. Okay. Now, thermodynamic properties, now if you remember, so these were, I am going to just write this out. Okay. So, now the point was to calculate the properties just behind the shock wave and on the surface of the cone. Now, the way it stands here, you can actually calculate the properties in the entire region, in the entire region here. You do not have to restrict yourself to just here and here. Okay, that is what is asked in the problem, but we can actually calculate it anywhere within this space. Now, if you look at this here, so this is the temperature, pressure, and density. Now, this Mach number, okay, now this Mach number corresponds to V dash. Okay, so that V dash is at every radial location. So, like we did over here, right? If you look over here, for at every radial line, we're going to have a V dash. So, we're going to have a V dash over here. So, V dash 1, V dash 2, V dash 3, 4, and so on and so forth. So, this Mach number actually corresponds to that V dash. So, when we go in step, so when we are basically going from step from here to this particular radial line, so then we can actually calculate the V dash here, okay, because we basically solve the Taylor-Macol equation for V r dash, and then we calculate the V theta dash using this, hence we can get V dash. Okay. So, once we get this V dash, so then we can input that in terms of the Mach number here, and we can get the thermodynamic properties. So, once we come, we keep doing this over the entire region here behind the shock, and once we come over here, so basically you're looking at the radial line, which is at theta c, which is the half cone angle. So, corresponding to that here, V theta dash of course should be 0, because it's the zero normal boundary condition. Okay, we will implement that. So, we have a V r dash is essentially V dash. So, then that is the Mach number which we should be implementing over here. Okay, that is the Mach number we are going to implement over here, and use these parameters, use these equations rather, to calculate the properties behind the shock wave. So, that basically is the entire procedure, okay, which is I think pretty simple as such. So, the first step is basically, we said we will assume theta s given Mach number. So, we get m2, correspondingly we put m2 into the equation when we get this V dash. Okay. Once we get V dash, then we come here. So, we calculate V r dash and V theta dash using Taylor-Macol equation and this, and we march away here. So, at various radial locations between the shock wave and the surface, we get the V r dash and V theta dash, and we calculate also the thermodynamic properties using these expressions, and when we come we implement the zero normal boundary condition when we come to the surface. That's pretty much it, right? The complicated part, or the majority of the work out here in the problem, is essentially here, isn't it? Essentially here in step 3, where we need to calculate V r dash, okay, using the equation 6. This is the Taylor-Macol equation, where we are going to basically use a fourth order right. What we are going to do is basically we are going to use a fourth order Runge-Kutta method, okay, to for here. So, what I will do is, in the next lecture we will basically go over that. Okay, we will go over this particular step where we use the Runge-Kutta method to solve the Taylor-Macol equation for V r dash. Okay, we will continue with that, and hopefully we should be able to complete the solution since there. So, this is basically the these steps, step 4, or yeah. So, I guess we can write this as step 5, and this is calculate thermodynamic properties. Okay. That is it. So, these are basically 5 steps and we are done. So, what we are going to do in the next lecture is basically go over in detail about the fourth order Runge-Kutta method and how we are going to use that to solve the Taylor-Macol equation. Okay, all right, that should be all. Thanks.